Welcome everyone. Today we'll explore about failure analysis of welded constructional steel component, investigating causes of defects in steel welds. Introduction to failure analysis, agenda and objectives. Failure analysis of welded constructional steel components is a critical process in structural engineering and metallurgy. It involves investigating the causes of failure in welded joints and components to prevent future occurrences. Welded steel structures are widely used in bridges, buildings, pipelines, and industrial machinery, making their integrity essential for safety and reliability. Failure analysis helps identify root causes such as material defects, improper welding techniques, environmental factors, and operational stresses. This process typically includes visual inspection, non-destructive testing, NDT, metallographic examination, and stress analysis. Understanding failure mechanisms ensures compliance with standards, reduces maintenance costs, and enhances structural performance. The introduction sets the stage for exploring weld stresses, fracture mechanics, weld characteristics, and common defects, culminating in preventive measures and conclusions. The agenda outlines the key topics of this presentation. Number 1, Introduction to failure analysis and its importance. Number 2, Weld stresses and their impact on structural integrity. Number 3, Fracture mechanics principles relevant to welded joints. Number 4, Characteristics of welds including microstructure and heat-affected zones. Number 5, Common welding defects and their implications. And number 6, Conclusions and preventive strategies. The objectives are to provide a comprehensive understanding of how welded steel components fail, the scientific principles behind these failures, and practical approaches to mitigate risks. By the end of this presentation, participants will be able to identify critical stress factors, interpret fracture behavior, recognize weld quality indicators, and apply best practices in welding and inspection. Types of weld stresses, impact of weld stresses on structural integrity. Welded joints experience various stresses that influence their performance and longevity. The primary types include residual stresses, thermal stresses, and mechanical stresses. Residual stresses arise from uneven cooling during welding, causing localized tension and compression zones. Thermal stresses occur due to temperature gradients during welding and subsequent service conditions, which can lead to distortion or cracking. Mechanical stresses result from external loads such as tension, compression, bending, and fatigue during operation. These stresses interact and may initiate microcracks or propagate existing flaws, ultimately compromising structural integrity. Understanding these stress types is essential for designing welds that withstand operational demands and environmental conditions. The combined effect of residual, thermal, and mechanical stresses can significantly reduce the durability of welded steel components. Residual stresses often remain locked within the material, creating weak points susceptible to fatigue. Thermal stresses can alter microstructure, leading to hardness variations and brittleness in the heat-affected zone, HAZ. Mechanical stresses, especially cyclic loads, accelerate crack growth and fatigue failure. Engineers must account for these stresses during design and fabrication by selecting appropriate welding techniques, preheating, and post-weld heat treatments. Failure to manage these stresses can result in catastrophic failures in critical structures such as bridges and pressure vessels. Principles of fracture mechanics, crack propagation and failure modes. Fracture mechanics provides a framework for understanding how cracks initiate and propagate in welded components. Key concepts include stress intensity factor or K, fracture toughness, and crack growth rate. When a crack exists in a weld, the local stress concentration increases, and if the stress intensity exceeds the material's fracture toughness, rapid crack propagation occurs. This principle explains why small defects can lead to catastrophic failures under certain conditions. Engineers use fracture mechanics to predict failure, design safer joints, and establish inspection intervals. Techniques such as finite element analysis or FEA and fatigue testing are commonly employed to assess fracture behavior in welded structures. Crack propagation in welded steel components can occur in several modes: brittle fracture, ductile fracture, and fatigue failure. Brittle fracture happens suddenly without significant plastic deformation, often at low temperatures or in high-strength steels. Ductile fracture involves noticeable deformation before failure, typically under high loads. Fatigue failure results from cyclic loading, where cracks grow incrementally over time. Weld defects such as porosity, inclusions, and lack of fusion act as stress concentrators, accelerating crack growth. Understanding these failure modes helps engineers select appropriate materials, welding processes, and inspection techniques to prevent unexpected failures. Microstructure and heat-affected zone, mechanical properties of welded joints. The microstructure of a weld and its surrounding heat-affected zone or HAZ plays a crucial role in determining mechanical properties. Welding introduces rapid heating and cooling cycles, resulting in heterogeneous microstructures. The weld metal typically exhibits columnar grains, while the HAZ may contain coarse grains and hardened regions due to thermal exposure. These variations affect hardness, toughness, and susceptibility to cracking. Alloy composition, welding parameters, and cooling rates influence microstructural development. Proper control of these factors ensures a balanced microstructure that resists failure under operational stresses. Welded joints exhibit distinct mechanical properties compared to base metal. Tensile strength, hardness, and impact resistance vary across the weld metal, HAZ, and unaffected base material. Hardness peaks often occur in the HAZ due to rapid cooling, which can lead to brittleness and crack initiation. Weld metal may have higher or lower strength depending on filler material and welding technique. Engineers must evaluate these properties through testing to ensure compliance with design specifications. Failure to account for property variations can result in premature failure under service conditions. Common welding defects, impact of defects on structural performance. Welding defects are imperfections that compromise the integrity of welded joints. Common defects include porosity, cracks, lack of fusion, incomplete penetration, and slag inclusions. Porosity results from trapped gas during solidification, reducing strength. Cracks can form due to thermal stresses or improper cooling. Lack of fusion occurs when the weld metal fails to bond adequately with the base metal, creating weak zones. Slag inclusions are nonmetallic particles trapped in the weld, leading to stress concentration. Identifying and preventing these defects through proper welding techniques, preheating, and post-weld inspection is essential for structural reliability. Welding defects significantly reduce the load-bearing capacity and fatigue resistance of steel structures. Defects act as stress concentrators, accelerating crack initiation and propagation under cyclic loads. In critical applications such as bridges, pipelines, and pressure vessels, even minor defects can lead to catastrophic failures. Regular inspection using non-destructive testing methods like ultrasonic testing, radiography, and magnetic particle inspection is vital to detect defects early. Implementing stringent quality control during fabrication and repair minimizes defect occurrence and ensures compliance with safety standards. Summary of key findings, preventive strategies, and best practices. Failure analysis of welded constructional steel components reveals that stresses, microstructural variations, and defects are primary contributors to failure. Residual and thermal stresses create weak zones, while mechanical stresses accelerate fatigue. Fracture mechanics principles explain crack propagation and failure modes. Weld characteristics such as microstructure and hardness influence performance, and defects like porosity and cracks act as stress concentrators. Understanding these factors is essential for designing reliable welded structures and implementing effective inspection protocols. Preventing failures in welded steel components requires a multifaceted approach. Key strategies include selecting appropriate welding processes and filler materials, controlling heat input to minimize residual stresses, and applying preheating and post-weld heat treatment to refine microstructure. Implementing rigorous quality control during fabrication and using advanced non-destructive testing methods ensures defect detection before service. Regular maintenance and monitoring of critical structures further enhance safety. Training welders and engineers on best practices and adhering to international standards such as AWS and ISO are vital for achieving long-term reliability.